Hello everybody, my name is Giuseppe Pinto and I'm a PhD student from Politecnico di Torino, and today I will present a paper developed with my co-authors here on list during a collaboration between Politecnico di Torino and University of Texas at Austin. The paper is entitled Towards Coordinated Energy Management in Buildings Using Deep Reinforcement Learning, and it aims to show how artificial intelligence could be combined with energy management to integrate buildings into smart city contexts. Nowadays, buildings are becoming more and more complex. Just think of the increased penetration of multi-sources HVAC systems, distributed renewable, and storages. While this increases the so-called energy flexibility, it also requires innovative management of such buildings. Moreover, control strategies must be able to handle user preferences and renewable uncertainties, no more in a reactive way, but predicting and adapting to new conditions. This concept becomes even more profound for clusters of buildings, where grid interaction must be handled. At higher level, there is therefore the necessity to enhance cooperation among buildings to increase energy savings, user comfort, and grid stability. The previous points could be achieved thanks to the novel concept of coordinated energy management. This concept arises from the necessity to manage the aggregated power demand of a number of buildings. In particular, it should consider integration of renewable electricity at single building level, the optimization of the cluster energy consumption, and the interaction with the grid, to reduce peak demand and increase grid stability. In this framework, energy management should leverage automated control strategies, able to adapt to a changing environment made up of different actors. After a literature review, we have seen that a lot of effort is devoted to single building optimization, and while some innovative works have tried to use advanced control strategy at cluster scale, such as heuristic control and model predictive control, they suffer from scalability problems due to their model-based nature. To overcome these limitations, we use an adaptive and potentially model-free control strategy, the deep reinforcement learning, with multiple buildings. This is done also thanks to the use of a novel simulation environment called CityLearn, built from the co-author of the University of Texas to test reinforcement learning control strategies for energy management. Finally, the paper explicitly assessed the potential benefit of a coordinated approach at three different scales, starting from the single building level up to the cluster and grid level. In the following slides, I will briefly introduce reinforcement learning, followed by the description of the case study and the framework developed during the work. Reinforcement learning is an area of machine learning often used in control theory, in which an agent learns a control strategy through a trial and error interaction with the environment. For sake of clarity, I will discuss an example that involves an energy system. Here the controller, called agent, is connected to a heat pump and thermal storage. The controller has the goal of minimizing electricity cost, represented by a reward function, charging and discharging the storage. After performing some actions, the environment provides the agent the correspondent reward and the information about the new states, for example, external temperature, cooling load, and the electricity price. The agent then analyzes the new information and provides new actions. Mathematically speaking, the problem can be defined by two functions, the state value function and the action value function, used to quantify the goodness of a policy. Finally, the goal is to find the optimal control policy that maximizes the return, defined as the sum of rewards over the control interval. The combination of reinforcement learning and high-capacity function approximators, such as deep neural networks, seemed to overcome computational problems related to complex state-space representation, leading to what is called deep reinforcement learning. In particular, the paper exploits a state-of-the-art algorithm called soft actor critic that takes advantage of the actor-critic architecture. With this algorithm, both state value function and action value function are approximated by two deep neural networks, shown below. Moreover, the biggest feature of the algorithm is that it uses a modified objective function in which the agent does not only maximizes the reward, but also the entropy of the policy, looking for robust control strategy, crucial for energy management. As previously said, the case study used a CityLearn environment, created from the University of Texas at Austin, to test reinforcement learning algorithm for energy management. In particular, the buildings are equipped with heat pumps and electric heaters to meet cooling and domestic hot water demand, coupled with chill and hot water storages. Moreover, some buildings also have PV arrays. In the bottom right figure, you can see how we selected 4 buildings with different profiles in both shape and intensity to highlight the heterogeneity of the built environment. Finally, we applied some changes to the environment, introducing a variable electricity price and the detailed modeling of the heat pump. The first step was to analyze the system, highlighting the possible flexibility sources. Here, we aggregated the cluster profile and identified PV production, cooling and domestic hot water demand, and the appliances loads. The goal was to optimally control the storages, taking into account the presence of the PV panels and the variability of the electricity price. To compare our algorithm, a manually optimized rule-based controller was created. The rule-based controller charged uniformly the storages during the night to exploit the lower electricity price and avoid sudden peaks. On the other hand, for the deep reinforcement learning controller, we created a specific reward function with multiple terms. The first term tries to minimize the sum of the squared energy consumption, limiting peak demand, while the second one considered the variability of the electricity price with the aim to reduce costs. Both terms are weighted using factor beta and rho to express the relative importance inside the reward function. Here is presented the developed framework, where first we analyze the single building level, focusing on optimal control of the storage to maximize the energy efficiency of the system. Moving at the cluster level, the diversity of the buildings is taken into account, considering the possible presence of local renewable and focusing on their integration, while reducing the peak demand. Finally, the control level merged the previous acquired information with electricity price and other external variables to provide a robust control strategy. The results of the analysis are presented at 3 different levels, starting from the single building up to the grid level. In particular, we focused the attention during the peak period of the RBC to compare the performance of our controller. Looking at the single building, we chose the control strategy for the 2 storages, analyzing their dependencies with external temperature and electricity price. While the RBC controller takes only advantage of the electricity price, charging uniformly the storages to avoid peaks, the DRL controller learned the dependency of the heat pump COP with temperature, charging the cooling storage during the coldest hour and discharging it during the hottest hour, while taking full advantage of the lower electricity price during the night. Moreover, it is interesting to notice how the charge of the 2 storages is shifted to avoid peaks even at single building level. At cluster level, it can be seen how an uncoordinated energy management may lead to peak creation during the night period to lower the cost of each building. On the other hand, the approach proposed is able to lower this peak while creating a more homogeneous electricity consumption over the day, useful to increase renewable electricity integration. Looking at the grid level, the load duration curve is used to highlight firstly the importance of the storages that increase the base load independently from the control strategy. On the other hand, however, the control strategy directly affects the peak demand that could even increase, underlying how the presence of storages could be a double-edged sword for the grid. Zooming on the peak demand, it can be seen how rule-based control has a higher peak with respect to the no storage case, while deep reinforcement learning is able to reduce maximum demand. The results of the 3 levels are summarized in the table, highlighting how the deep reinforcement learning is able to outperform the manually optimized rule-based control. In particular, there is a 4% energy reduction due to the ability of the controller to assess the dependency of the heat pump with external temperature. On the other hand, electricity cost reduction is mainly due to the lower energy consumption, since RBC was manually optimized to obtain the lower cost. However, the most interesting differences are in the maximum peak reduction of around 8% and the average daily peak, with a reduction of over 15%. Finally, the proposed approach is also able to decrease the peak-to-average ratio of around 5%. Now, I'd like to introduce the conclusion starting with some quotes that gave us the foundation on which the work is developed. The first one is from Aristotle, that wrote, "The whole is greater than the sum of its parts." The presented papers clearly show how it is important to see opportunities beyond multiple buildings, and that the coordination among them could bring advantage to the community. Moreover, the model-free approach ensured the scalability of the process. Secondly, Joseph Stiglitz said that what we measure affects what we do. In particular, the design of the reward function that the agent measures strongly influences the DR controller behavior. Therefore, it is necessary to find the optimal trade-off among different objectives that must be pursued. Lastly, Albert Einstein once said that the measure of intelligence is the ability to change, and I want to highlight how the trial and error approach provided the agent with something similar to intuition while searching for optimal policies, understanding the dependency of the systems. Additionally, the adaptive nature of the control can be used in rapidly changing environments, for example, with demand response programs. Now, what lies ahead? In the near future, we decided to improve the current environment and further explore the advantages of deep reinforcement learning. In particular, we will analyze the effect of the reward function definition on the scalability of the process and work on the comparison of several deep RL architectures to fully understand the advantage and disadvantage of each one. Additionally, we are interested in analyzing energy exchange among buildings due to renewable overproduction and the resulting changes in the control strategy. All this while we are currently working on the introduction of comfort metrics in city-learn environment using black box models. Before concluding, I want to thank my co-authors, Professor Alfonso Capozzoli and Silvio Brandi, for guiding me along the way, and Professor Zoltan Nagy and José Vázquez Cantelli for their comments and their credible work behind CityLearn. If you are interested to the topic or want more detailed information, check out our paper and feel free to write us an email. Thank you for the attention.